So, all right. I'll just raise my voice. So, for all those of you who've come, you're in for a treat. For those who haven't come, you missed it, but since you're not listening to me, it doesn't matter. Hopefully there's some people out there. So today we have Mark Raizen, who is the Sid and Richardson Foundation Regents Chair in Physics. And he got his BS degree in mathematics at Tel Aviv University. He started continuing in mathematics at the Weizmann Institute. And then he went to the University of Texas to work with Steven Weinberg. And after a year, I guess he saw how much more important experimental physics was. Just kidding. Anyway, so he started to work with Jeff Kimball at University of Texas, who was then there and then moved to Caltech. And from there, he did a postdoc with Dave Wineland at NIST. And so with Jeff Kimball, he was one of the early pioneers in the squeeze states, following, I might add, in the footsteps of Dick Slusher, Bernie Yerke, and our own Leo Holberg, who did the first squeezing. I think you guys were the second. He looked at Rabi vacuum splitting. He developed miniature ion traps with Dave Wineland. It's become one of the technologies for quantum information. He developed applications of laser cooling trapping, which you will hear about today, dynamical localization of momentum of atoms, quantum suppression of chaos. One of the things he's perhaps not as well known for, but which I'm a great admirer of, is his experiments looking at ordinary Brownian motion, but with such high spatial and temporal resolution, he can actually see the transition from ballistic transport, meaning in between collisions in a gas and then in a liquid, to diffusion. And so, which is a real technical tour de force. He's got the Willis Lamb Award in Quantum Optics in 2008, the Max Planck Award in 2002, the I.I. Rabi Prize in 1999, and sure, more to come. So, Mark,
thank you, Steve.
Yours.
Thank you. And it's a pleasure to be here. Thanks for coming. Can people hear me in the back? Okay, great. Okay, so today I will tell you a story about the isotopes, Maxwell's Demon, and the Pointsman Foundation. I'm sure you have heard of the first two, but perhaps not of the third. Okay. Let me start with isotopes. So the word literally is equal place. It was coined by Frederick Soddy, who discovered it. Actually, apparently it wasn't coined by him, but a family friend who suggested that, and the name stuck. Isotopes imply that they are the same element, but different number of neutrons. Illustrated here with two that you know and love. Carbon, carbon-13 is about 1% abundant, actually 1.11 to be precise, and the rest is carbon-12. And this picture shows a chunk of coal and a diamond. And if I told you that this is made of carbon-13, you couldn't tell the difference, probably, because isotopes have almost the same physical and chemical properties. Not quite, and that's an important distinction. There we all have our periodic table. We know the periodic table quite well, but perhaps you don't know that there are as many as 254 stable isotopes. So many elements have multiple stable isotopes. Some are monoisotopic, like gold, at least stable. But what has made isotopes really important and interesting beyond the stable isotopes are the possibility of transmutation. And that came about around the 1940s with the invention by Lawrence of the cyclotron, using high-energy protons to bombard a target, or nuclear reactors where neutrons bombard a target, and you can take a element and you can transmute it into a different element, often a short-lived radioisotope. The workhorse of this field is called radiochemistry, and I'll say more about that, but it's a method to take the target and the produced isotope, radioisotope, to separate them chemically and extract it where it can be useful, typically for medicine. So I will talk more about these applications, but generally isotopes are a great resource. I thought of calling them a great natural resource, but some of them are not natural, so I could call it a great supernatural resource. But they have been used, or are used today, for cancer therapy. I'll talk about that, and preventing malnutrition as tracers. These are stable isotopes. Medical imaging, and basic science. And there's a long history of basic science, but I'll tell you about some recent fundamental studies that we've proposed. The key question, though, that I will address is how do you separate isotopes of the elements? Because they are nearly identical, so that's considered a hard problem. They have almost the same physical and chemical properties, and so you rely on very tiny differences, and that usually means it's a very difficult task.
Which is good in many ways.
I'm sorry?
Which is good in many ways.
It's good and it's bad. I mean, for some isotopes, of course, there's a risk of proliferation, and I could say more about that. But it's held back. It's held back their use, for example, in medicine, in a pretty serious way. Now, the workhorse for isotope separation is something that is not as widely known. It's called the calutron. I actually asked, what is the source of that name? Apparently Lawrence came up with the name. At first, what I was told is that it means CalU, which is Berkeley, and tron means tron, cyclotron, calutron. So it's a machine that was invented for the explicit purpose of separating uranium isotopes. This was done around World War II. After World War II, it was not used anymore with the development and invention of the gas centrifuge, which is what is used today to separate uranium hexafluoride. But the calutron remains as a general purpose machine because it works on essentially any element. It's like a large mass spectrometer. You have, and this is not shown to scale, but typically the scale can be many cubic meters of volume, where you have to maintain a magnetic field of a few Tesla. So that's why it's very energy intensive. You take a source of atoms, you evaporate them, and you ionize them with electron bombardment, and then you have an electric field that accelerates them, and they're in a magnetic field, which causes them to move in a circular orbit, depending on their charge to mass ratio. So the lighter ones have a smaller turn ratio than the heavier ones, and you collect them in pockets, and that's how you separate the isotopes. So this is a schematic, but in fact, the original calutrons were built in the 40s, and the technology really has not changed in any fundamental way, as far as I'm aware. Of course, they use diffusion pumps now. Maybe they still use diffusion pumps. I think the modern calutrons are kind of 1950. But in the U.S., what happened was that the calutrons were first developed in this country. The biggest ones were in Oak Ridge. But because they were so energy inefficient that eventually they were shut down. And I don't remember when, maybe in the 90s they were shut, late 90s, I think the final large calutron was shut down in the US, leaving a shortage of isotopes. And today the only large calutron facility in operation is in Russia. And when I gave this talk a few years ago, I pointed out that that's a kind of a fragile situation. Now with the war in Ukraine, I don't even need to say that. It's actually created a true crisis of supply. And so there is an urgent need for new methods. Now, people have constructed newer calutrons. They're called mini calutrons, but it's essentially the same technology. It's nothing really new there. And so that's sort of the background for this talk, is that we now have a crisis of supply. This was highlighted by several reports to DOE, by the Nuclear Science Advisory Committee, alerting that there will be severe shortages of many isotopes used in medicine. All right, before I go into how we might address that, I want to step back and go back in time to this man, James Clerk Maxwell. Needs no introduction. He was Einstein's hero, so that already tells you that perhaps one of the greatest scientists of all time, known mostly for unifying electricity, magnetism, and light. But late in his life, when he was at the ripe age of 40, he was born in 1831, died in 1879, he was pondering over questions of thermodynamics and statistical mechanics, and he had an idea, a thought experiment. We have a long tradition in physics of thought experiments. Actually, he didn't coin the term Maxwell's demon. That was coined by his friend, Lord Kelvin. Apparently, he hated the term because it sounded very spooky. Demon. And I'm sure you've all seen something like this. I lifted this picture from Wikipedia, but it is indeed a spooky picture, and it shows the idea was that you have a chamber full of gas molecules, and you divide them into two halves, one you call A and the other B, and there's a trap door. And the trap door is operated by this creature, the demon. You can see his horns and a little beard. And this demon has a flashlight, a magic flashlight, with which he can see the coming and going of every gas phase molecule. And if a molecule's moved, for example, the demon could do several different things, the different versions of the demon. One of them is you could call it the pressure demon, where the demon would, if he sees a particle from B going towards the barrier, he opens the barrier and lets it through, otherwise keeps it closed, and in such a way would cause all the gas molecules to migrate from B to A. Everything now is concentrated in A without changing their kinetic energy. So this is very different, say, than adiabatic compression or anything like that. Clearly, that reduces the entropy of the gas because you haven't changed its velocity distribution, or kinetic energy, but you've now restricted to a small volume. And now, so this, I would say, if you believe this picture, then I have another picture you might like, and it's this one. Because they're just about as fantastical. And so, and maybe some of you do believe it, and my apologies if so. But let's go back to this picture because I want to make a few points about it. One of them was that people have certainly done what I would call demonstration experiments at the single particle level, where you could maybe, rig it up with ultra-sensitive detection, cavity QED, or some other method, or you could use, instead of single molecules, you could use little nanospheres or microspheres. But that is not the spirit of Maxwell's demon. Maxwell's demon really, as far as I understand, I think Maxwell made it clear, it's about large ensembles. So you really want to start thinking about, the thermodynamic limit of Avogadro's number of particles. And this led Maxwell to actually say, this is impossible to us. That was back in 1871. So we've made a lot of progress since then. But nevertheless, I would say that there's been 150 years of controversy surrounding this thought experiment. The first thing that people wondered is, aside from the practicalities, does this violate the second law of thermodynamics? Because certainly you are lowering entropy of the gas. Where's that going? And I think the first to explain that was Leo Szilard in 1929, when he introduced the concept of information entropy. And he argued that the demon must collect information. That information has, he assigned it an actual physical quantity of entropy, and as the entropy of the demon goes up, the entropy of the gas goes down, and so you save the second law. This was revisited by Rolf Landauer at IBM and Charles Bennett also there a little later. Landauer argued about is it really irreversible, and he invoked the idea of erasure of information, that if you store it in some registers, you must erase it in order to make it truly irreversible. But I would say all of this, from an experimentalist point of view, left something to be desired, because you could still say, okay, conceptually we can believe that we're not violating the second law, but this still seems crazy, right? And the objections you might come up with are, first of all, could you really do advanced detection of each particle? I mean, think about the difficulty of doing that. I mean, not just one, but Avogadro's number, say. And then, not to mention the operation of the gate. And now you'd have to include all the energy that's required to operate a gate. And so I think that it's fair to say that this picture is still impossible, at least as far as I can tell. I mean, if someone thinks they can do it, great. But there are so many problems with this picture that, you know, there's a saying that a picture is worth 1,000 words, but I think in this case, a bad picture takes many more words to correct. And this picture of the demon, the intelligent demon, in my view, is a really bad picture, because it leads people astray to think that that was the intention, or that is even possible. So, you know, you sort of say, well, what's the conclusion? Is this just some idea that will never happen? Or is there really content to Maxwell's demon? You know, we have other thought experiments like Schrodinger's cat, and you know, you've heard stories about how we're moving towards making larger superposition. But today, my message to you will be that we can realize Maxwell's demon precisely, and we get rid of the spookiness. Sort of two benefits. Okay, so the question that we posed, and I'm sort of looking back and surprised that it's already been 18 years ago, so time flies, was the following question. It really wasn't motivated in any way by Maxwell's demon. At least I wasn't thinking about that in that context. It was just a curiosity-driven question. Can we make a one-way wall for atoms? So what would that mean? It would mean some barrier that breaks reciprocity, that atoms could go one way, but they couldn't come back. Could you do that? Well, started thinking about that. Why would you want to do that in the first place? I don't know. It just seemed like a cool thing that if you could do that. You call it a diode for atoms, for example. But truly irreversible in a way that it would do just that. Well, so we came up with, actually, with a way to do it. We proposed this in a paper. It was published in 2005. We actually had a hard time publishing this, and the one referee A, who I hope is not in the audience, gave all these objections why this could never work. And then I answered the concerns, and in the second round, this referee said that he agrees, or she agrees, that it can work, but it's trivial. So, but in the end, the editors were finally convinced, and then we published it. But the key thing, I think it's a simple idea, but it relies on two important ingredients. The first is that you need a conservative potential, but a conservative potential will not break reciprocity. So like a magnetic field, there's no directionality involved. The second part, though, is necessary, and that is you have to have an irreversible process, and the one that we propose, that atomic physicists love, is optical pumping. So maybe apologies to the experts in the audience, and there are many here, but let me explain a little bit how that works. But the key thing is that the operation of this one-way wall does not utilize the momentum of the photon, but rather the photon entropy. And I'll say more about that in a little bit. It uses actually in a very minimal way. So what is the smallest amount of entropy that is actually required for this kind of one-way wall to work? So, sorry, it keeps split. All right, so optical pumping was proposed by Alfred Kastler. Actually, he called it literally, I'm not going to try and pronounce the French because I'll embarrass myself, but it's cooling by light. And what he meant by that, I think, is it was cooling the internal degree of freedom of an atom, not the translational motion. But what that means in practice is that suppose you have the following setup, which we see all the time in atomic physics. We have a source of atoms, an atomic beam, with diverging rays coming out. So these are atoms coming out, and we have a laser beam where we can choose its polarization, and here it's sigma plus, right circularly polarized light. And let's consider a simple two-level atom with j equals 1 to j equals 1. So there are three states. I'm sorry, I should have put the +1, 0, and -1, so it's m. But you get the point. It's three states that are thermally occupied coming out of the oven, equally occupied statistically. And now but after they are cycled several times by the laser, the optical pumping laser, By using right circularly polarized light, the transition rule is delta M equals +1 on absorption, and then it decays down spontaneously, shown by the squiggly line. And after several cycles of absorption and emission, you populate entirely into the +1 state. Now, if you were to choose left circularly polarized light, you could put it into the -1 state, or by losing linear, you could put it into the 0 state. And so we can control completely the way an atom responds to magnetic fields simply by choosing the right laser to do this. Okay, so now if you look at from an entropy standpoint, this is a single state, so this is an entropy 0 state, and this is the maximum entropy where it's equally distributed. Okay, so how does this one-way wall work? Let me walk it through because this really is simple, and I think it's illustrative to explain it in this toy model. So in the toy model, we have our canonical box divided, well, the particles I got tired after pasting in 16 dots, so this is a 16 not thermodynamic limit. But it illustrates it. So initially, we imagine that they're equally distributed randomly inside this box. Let's first pump all the atoms to the M equals 0 state with optical pumping. So that's the initial state. And now we turn on a magnetic field in the center, shown in green. Now you ask, what happens? And the answer is nothing, because the atoms are in a non-magnetic state, so they simply don't see the magnetic field. They can move back and forth as if it's not there. Okay, but now let's turn on an optical pumping beam that takes atoms from the M equals 0 state and converts them to the M equals 1 state when they cross. Now what happens? And the ordering now matters. So I'm showing shown in orange is the optical pumping beam, is to the left of the magnetic field. So atoms that were on the right, if they're moving to the left, they cross the green line, they don't see it. So they just go right through. Then they hit the optical pumping where they're converted to red dots. Red signifies M equals 1. Now, if they try to come back, they see the green as a repulsive barrier and they're turned away. So they can't come back. They can't go to the right. Now, if they are already on the left side, in the M equals 0 state, as they're going this direction, they'll hit the optical pumping beam, they'll be pumped in the M equals 1 state, and they also get reflected back. So if you just wait in this picture, in this one-dimensional picture, everything migrates to the left-hand side, and the only penalty you pay is the scattering of a few photons, which I'll argue is a negligible, depending on, of course, the temperature of the atoms, but typically is a very small number, so we can kind of neglect that. The heating is very small. All right, so this is an idea. Now there's a simple argument involving entropy, and I have to say entropy. You have to be a little careful because we have a process that is non-thermal. It's not thermal equilibrium. So nevertheless, I think it is fair to say that the distribution is thermal. It started out thermal, but now we put it into a smaller box. So clearly, there is sense of entropy. But what we can account for that in the following way, that the laser beam is a source of very directed photons. They're all going in the same direction in one mode. So they have 0 entropy in the laser. That's what characterizes the laser. But when an atom takes that photon, absorbs it, and spontaneously emits into free space, it has increased the entropy of the photon, because now it's in a random direction. And you can calculate that, and we did in this little paper here, and found that there's detailed balance. That is, the entropy of the gas goes down, and it's exactly compensated by the entropy of the photons that goes up. You don't really care about them. They go off to infinity, or they get absorbed by the walls. We don't have to see them, but they are the things that are carrying away the entropy. So in a way, the laser serves as a source of entropy that saves the second law. Now, being an experimentalist, you have an idea, and it was a toy model, a one-dimensional toy model, but real life is 3 dimensions, and so you have to do an experiment. And we did the experiment in my group, and we were able to take atoms that were initially used laser cooling to confine them, and then we tried to compress them in phase space, And we saw a large enhancement. Actually, in this experiment, it was a 25 times, but in a subsequent paper, not cited here, it was 350 times increase in phase space density. So it was a big effect, and it was clearly not laser cooling because it was only scattering on the average, a few photons per atom. All right, so the downside, although there was a large compression of phase space, we were not really conserving atom number because it wasn't really working in 3 dimensions properly. So we thought about this more, and in 2014 wrote a paper, first paper, and then just recently in the summer we had some insights on how to do this even more efficiently, and that paper is submitted. I call it magneto-optical cooling, or MOP cooling, and there's a picture of a MOP because it kind of works that way. In a way, it's like the impatient demon. The patient demon might just wait till the particles come to the wall, but an impatient demon doesn't want to mess with all that. So let's just start shoveling things around. But it uses the same toolbox of optical pumping and magnetic forces. So that's what we're doing, cycles of optical pumping and magnetic kicks. The heavy lifting, if you will, comes from the magnetic kicks. And we've learned in my group how to impose very large magnetic fields and field gradients. So just to illustrate how this works, MOP cooling for the j equals 1 state, if we only concentrate on m equals 0 and m equals 1, then if we have a cloud and we imagine we release it, so now it's free to expand. So we have to do everything fast compared to free space expansion and to gravity. So it's got to be a fast process, but as long as we do it fast enough, we're not going to lose phase space by free expansion. We have some spatial extent delta x0. Now we optically pump in a way where we spatially shadow, we illuminate half of the cloud. The other cloud is not illuminated. So that optically pumps the right side into the m equals 1 state, but we leave alone this half. Now we apply a magnetic field gradient, which is going to, like a push-pull, it's going to pull one, well, it's actually not going to affect the m equals 0. It's going to leave it alone, but it's going to exert a force on the m equals 1, and they're going to start to merge. Of course, if we don't do something, it's going to overshoot, and they're going to just fly by each other. So we have to reverse the kick, switch the sign of the currents, and bring them to rest exactly when they're overlapped here. Now you see the colors merge, but then we complete the cycle by optical pumping, which is an irreversible step. And if you look at the beginning and the end, we've taken this cloud and we've compressed it by a factor of 2x. So now that sounds good, but it's not great if you take into account realistic parameters where there can be some free expansion in the other dimensions. And there's a subtlety here which I don't have time to describe. How do you apply a one-dimensional magnetic kick? That's something that we worked out with Dima Butker's help especially. It's a dynamical averaging effect because you can't make a purely 1D gradient. Maxwell's equation doesn't allow that, but nevertheless you can make a one-dimensional kick by adding a bias field plus a gradient. And probably experts know this already. But then I had an insight in the summer, and I was sort of kicking myself that I didn't think of this earlier, but luckily no one else did either, so it's okay. And that is, suppose we have a higher spin, not j equals 1. Here's a small extension, j equals 2. Well, in a j equals 2, there's 5 possible spin states, plus 2, plus 1, 0, minus 2, minus 1, and minus 2. So we start with a cloud shown in purple, and now we use stimulated transitions to tag them. Each color here is a different spin state. So let's say this might be plus 2, and this one's minus 2. Now we do the magnetic compression, and the outliers are going to get a bigger kick than the inliers, so they'll all converge at the same time, and now we've shrunken the cloud to 5 times smaller, but they're mixed. But then we can optically pump them back to the initial spin, and thereby we've compressed by 5x. Now, we were actually thinking of using atomic dysprosium where j equals 8, so that's 17 times. Now this is in one dimension. This would be the compression you could get in one spatial dimension in one cycle. Now, so you can imagine doing this in x, y, and z several times, and you could get, in principle, large compressions. We don't know the limits of this, so we're not sure yet how far we can take this. All right, so now maybe, since I teased you a little bit with Maxwell's demon, it's fair to ask, is this Maxwell's demon? Right? It's certainly not the standard picture of Maxwell's demon. So, but on the other hand, it works exactly like Maxwell's demon was supposed to work. You have a cloud and you magically get everything to move to one side. So it looks like it worked. I would say it passes the duck test. If it walks like a duck and quacks like a duck, it's a Maxwell demon. Right? But then the other question you might ask is, what would Maxwell say? And you might say, how could you possibly know that? Well, it turns out back in the far past, the younger people here don't remember that you actually write with a pen on paper, but people wrote letters to each other with fountain pens or quills on parchment paper or some other kind of paper. And Maxwell was a prolific writer, and he wrote a letter to his good friend John William Strutt, who became later on Lord Rayleigh, and I'm sure you've heard of Lord Rayleigh, and he wrote to him, "I do not see why even intelligence might not be dispensed with, and the thing made self-acting." So a self-acting device is exactly a one-way wall. So Maxwell had the correct intuition, he just didn't know, he didn't have the toolbox, he didn't know how to do it. But I think that was the only way, as far as we understand, that he saw that this could work. The other ways are so impossible, and I would think they really are still impossible. But it doesn't matter. And so the takeaway message from this part of the talk is that we have settled the question of Maxwell's demon. It just works. It's a self-acting device. It's just, in our case, it's just a laser. And you don't have to think about it anymore, really. I mean, people still debate it. I go to conferences and they say, people are wringing their hands, so we don't really understand Maxwell's demon. And I kind of get impatient with that because it doesn't matter. This is really work. It works. All right. So the future applications of this work are. We think that this could be an alternative to evaporative cooling of atoms, and we don't know yet if it would be a complete. Of course, getting all the way from laser-cooled atoms to a quantum degenerate gases, the stumbling block has been evaporative cooling, because you throw away typically 99.9% of your atoms, and it's a very slow process, and many times it doesn't even work. So it would be, I think everyone would be happy if we could at least partially get rid of evaporative cooling, because that could allow you to realize ultra-bright atom lasers, really high flux. And we predicted, we haven't realized this yet, but the proposal that was funded by Keck Foundation, that we could get a million-fold improvement in the flux of an atom laser compared to state-of-the-art, which is kind of like around 10 to the 5 atoms per second or so. But now we are revisiting this. We have a proposal, which we'll see if it gets funded. I'm not sure, but we tabletop physics tests of fundamental physics, which require actually extremely large Bose condensates. And I'm part of a team, including Dima Butker and several others, proposing an experiment with dysprosium condensates that could actually test how general relativity and quantum mechanics works together. So this would be pretty fundamental, but it really requires a very large atom number. And so that's a key thing. So I guess the point is that these methods, a lot of the community, cooling and trapping community has moved towards very small atom number, like quantum simulators, where you might have hundreds or thousands of atoms. This is the opposite extreme, where you may want to have extremely high number for precision measurements for atom interferometry, perhaps atomic clocks, but it potentially could get us to much, much higher flux. All right. Now to in some sense, the thing that I started from is isotopes. Because around 2008, when we were working on this, on the cooling, I don't remember what triggered me to think about it, but I started thinking that maybe these same methods could be used to separate isotopes in a different way than had been done before. And we called this magnetically activated and guided isotope separation, or MAGIS for short. And we proposed at the time that this is a replacement for the calutron, really the first practical replacement for the calutron. And I believe that now more than ever. Turns out that Maxwell was very much inspired by something that he observed on a daily basis practically when he took the trains, which was the mode of transportation in many places, the 19th century British Empire. There was a very important position called the Pointsman. This was the person that was responsible for switching the train tracks. And so if you had a train shown here going one way, the Pointsman would switch the track and cause the train to move another direction. And Maxwell was really inspired by this because he saw it as something that where human will or human intervention could change the future. So it's a very different perspective, say, than Newtonian physics. And so he was fascinated by that. And you can tell that, and I know all this because I have a friend who's a historian of science and an expert on Maxwell, actually writing a biography now of Maxwell. But he gave me these quotes from letters that Maxwell wrote to his friends. The first was from 1868 to William Thomson, who later became Lord Kelvin. He's the guy who came up with the nasty name Maxwell Demon, in which he says, "Now let an intelligent but finite and energy-conserving being be appointed pointsman to the flying molecules." Right? And then in his other letter to, this was the same letter that I quoted earlier to Lord Rayleigh, he said, "Like a pointsman on a railway with perfectly acting switches who should send the express along one line and the goods along another." So this was central to Maxwell's thinking of the demon, what became known as the demon. but on a situation where you're not in a confined box, but in some sort of tracks that you could go on. So the way we view this as MAGIS is the atomic pointsman, a variation of Maxwell's demon, but applied to not to a cooling process, but to a sorting process. That's also an entropy reducing activity. I mean, and so it's interesting from the standpoint of entropy, when you demix something, that reduces its entropy. So let's take this picture and shrink it down, 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 down. And that's the smallest font that I could find. And now we've made the atomic pointsman is these atoms flying through, and we can do something to them to alter their directions. And what we do is, this is a schematic in very general sense of how this works. And you didn't really need, everything I'm telling you is kind of a story, but I could have skipped over all of that and just showed you the result, but maybe it wouldn't have been as entertaining. And I think it gives some insight, at least. I like history of science, and so I found this compelling. But the idea was also pretty simple. Let's imagine we have a source of atoms, a crucible, an oven, and we make an atomic beam, and we have a collector somewhere here, not shown. Of course, if we have a line of sight from the source to the collector, all the atoms get through. But suppose we arrange an array of permanent magnets, and we actually flip their sign we flip them by 90 degrees, so that creates what's called a Hallbach array, which maximizes the magnetic field on one direction. And we put them into a pattern that's slightly curved. So because it's slightly curved, we restrict, there's no line of sight, and it's not shown perfectly here, but imagine we block the line of sight, so there's no line of sight from the collector, from the oven to the collector. And so what we can do is we can use a laser. This is the optical pumping. This is the Pointsman. We can optically pump a desired isotope into a magnetic state that is a low field seeker. So when it comes close to this magnetic array, we can create surface fields on the order of a Tesla. Then it is actually reflected away, and now we break that line of sight, so now it can reach the collector. Other atoms, either they're non-magnetic, so they just go straight, or they're in a high field seeker in which they're pulled into the magnet. And so using this idea, we can analyze this, which we did. And first of all, the advantages of MAGIS are optical pumping, because we're utilizing only a few photons per atom. And that's important when you start to think of separating a mole per year, say, because that's Avogadro's number. And so you can't be as sloppy. Apologies, Steve. You can't use them many photons as you do in laser cooling. I mean, you don't mind if you're trying to cool 10 to the 8 atoms. You don't mind expending 10 to the 6 photons per atom. But if you're really wanting to collect 10 to the 23 atoms, you can't spend 10 to the 29 photons. It just not practical. You would need unreasonable laser power. So this efficiency of photon use is very important. We separate by the magnetic field acting on the magnetic moment. So unlike the calutron, which is separated by charge to mass ratio, the charge is always the same. The masses of isotopes are different by, like 1% or 2%. So the charge to mass is only slightly varying. But we separate not by charge to mass, but by magnetic moment to mass. And in fact, you can just neglect the mass differences. By optical pumping, we can even change the sign of the magnetic moment. We can make it 0. And so we have a big lever arm, and that means we could do this in a short distance and get very high separation factors. We're using surface magnetic fields with permanent rare earth magnets, so we're not drawing any current. And really the only energy we're using is to vaporize the material. And I think one of the most exciting things, which I'll say a little bit about at the end, is the possibility of hot separation as an alternative to radiochemistry. So I started this talk by saying the 3 pillars of all of isotope work is the transmutation, cyclotron and reactor, but then the 3rd pillar was radiochemistry. And my message to you today is I think we can replace radiochemistry. So we proposed this first on highly depleted lithium, which is actually used, lithium-7, very pure lithium-7, which is used in cooling water in nuclear reactors. We analyzed this and predicted that we could get an isotopic purity of over 99.95% in a single pass. And then we demonstrated this. It was published and patented, and it performed like we expected. So then, but the key things I want to emphasize is that this checks the boxes in terms of simultaneously satisfying different conditions. One of them is isotopic purity, scalability to required quantities, which in our case is around a mole per year of something, efficiency and cost, and general applicability. We've shown that MAGIS can work at over 80% of the periodic table. It's important to point out that you must satisfy these things simultaneously. And there have been a lot of proposals for isotope separation, and you can do one at the expense of the other. For example, if you took an atomic beam and you collimated to a divergence of a microradian, for example, you could achieve separation very easily, but your flux would be negligible. So you must, you can't sacrifice one for the other. That's kind of not a fair thing to do. So you have to satisfy all these together. At that point, around 2015, I wondered, where do we go from here? I mean, in academia, usually you do things, you publish papers, and then you move on to something else. But in this case, the more I learned about the necessity and the importance of it, I realized that it was important to move beyond just an experiment, a proof of principle. We actually had to do it. And I didn't really want to I didn't want to make a company. The university said, why don't you just start a company? And I just didn't like that approach. And also, as I'll show you, there are things that the important uses of isotopes that don't even have a business model, that will actually just cost money and not make money. So instead, I decided that we're going to start a nonprofit foundation, and I called it the Pointsman Foundation for historical reasons. So the Pointsman Foundation is a non-for-profit research organization. Initially, I mean, our initial work right now is centered around MAGIS technology towards isotopes, but the bigger vision is not limited to that. That's just our starting point. And so we have a board. I'm chairman of the board, and so on. Stephen Abrams is a valued member. He really co-founded it with me. He's a pediatrician. And an expert, as I'll show you, in micronutrients and infant health. Mark Epstein is our plastic surgeon. He's very involved in or concerned about infectious disease. Peter Fox is a radiologist, expert on medical imaging. Joe Jurczyk is an oncologist at Columbia Medical School, expert on targeted therapy with isotopes. Marianne Rankin, some of you know, she was dean who actually supported, when I first came to her, she was my dean in natural sciences, and I explained to her what we are doing and that we needed some internal support, and she just gave it to me. I mean, it was really a it was, she bet on it, and that got us started. So I'm really indebted to her. And then she became provost at University of Maryland, and she's a tremendous supporter. Doug Stone is, some of you know, a professor at Yale and also a big friend and supporter. We have a great advisory board, including Steve, Ted Hench, Ray Orbach, Neil Lane, Dave Reitze, Philip Toralva, an anesthesiologist, Eli Elbanovich, and Daniel Zeifman, past president of the Weizmann Institute, who's also very interested in us starting a lab in Israel. So let me, in the time that remains, and I guess I have about 10 or 15 minutes, is that okay? Let me talk about some of the applications. So cancer therapy, there is a great promise of targeted radioisotope used for cancer therapy. And the idea is that you take a targeting molecule like a monoclonal antibody that is designed to attach to something that's expressed by a tumor, or even if it's metastasized, and we or the medical community has learned how to chelate or attach it to a radioactive isotope that decays and emits a high energy particle, a beta or an alpha, and a gamma for imaging, and that will locally kill the tumor. This has really taken off, and of all the isotopes, one that has really stood out in the last years has been lutetium-177. This is a isotope. Lutetium is a lanthanide, a rare earth. It has a half-life of about 1 week. Emits a beta emitter, maximum energy of half an MeV, which translates to about 1 millimeter in tissue. And it has some gamma emission for imaging. And it is approved for various cancer therapies, but there's also many pipeline drugs being developed around lutetium-177 because of its favorable properties. The way it's produced today is you have to have a stable target, and one path is to use ytterbium-176, which is a stable isotope of ytterbium, which is just 1 over in the periodic table. It absorbs a neutron in the reactor, converts to ytterbium-177, which very quickly in under 2 hours decays to lutetium-177, and that lives for about a week. The alternate path is to use lutetium-176, and the nuclear cross-section is enormous. It's over 2,000 barns, but the downside is that there's two downsides. One is you're making a metastable contaminant, which has a 160-day half-life, and it's a gamma emitter, so that's a problem. The other is that you have no way of separating these two to give you a high specific activity product, because radiochemistry cannot separate those two. So people right now are all using ytterbium. But luckily, MAGIS is ideally suited to ytterbium because ytterbium has a zero magnetic moment in the ground state. So although it has many isotopes, if we don't do anything to it, it won't get through these curved arrays. So we don't have to use lasers for the unwanted isotopes. We just don't touch them, and they don't get through. We have a low low is relative speaking, but a few hundred C, maybe 400 C temperature oven. It's non-toxic, and we can pump it to the metastable state. So we love, I think there's other people in the audience who also love ytterbium for different reasons. But it's a nice starting place. We incubated this at the university. We have now reached a purity of 99.8%, and probably will get to higher, 99.9% in a single pass of ytterbium-176. We have a partnership with Eckert & Ziegler. They're a company, international company based in Germany. We have an exclusive supply agreement with a for-profit company which is majority owned by the Pointsman Foundation. So this was an important thing that I was hoping to do, and luckily we were able finally to do it by incubating it with philanthropy and internal money. We avoided the pitfall of having investors control us. And so that was an important step. It's a little over a year ago. And there's been a huge investment. Novartis, the huge pharmaceutical company, has invested many billions of dollars in drugs using lutetium-177, most notably for metastatic prostate cancer. So let me come back to radiochemistry. And I told you that's a pillar of the field of medicine with isotopes. And as a physicist, I feel somewhat uncomfortable. I don't really like radiochemistry, and I can't really tell you why, but except that I don't know enough chemistry, and it just looks really complicated and dirty to me. And maybe that echoes how other physicists field. If there's chemists in the audience, my apologies. I thought it would be appropriate here to quote Arthur Shallow, being from Stanford, who notably said that about molecules. At least that's what I read that he said. And maybe I share that same feeling. Maybe, maybe that's just ignorance. I don't think that's a good enough reason not to like radiochemistry. There are better reasons. And the main reason is that when you look at, for example, ytterbium-176 to produce lutetium-177, the problem is that they are so similar chemically, because the lanthanides are almost really very, very similar chemistry, that the radiochemistry is not that efficient. And so you lose about 15% of the ytterbium when you do the separation process. And that means that you can't really recycle your ytterbium very much, maybe 2 times, and you lose it, and you throw it away. But we believe that MAGIS can separate, instead of using radiochemistry, we can do physical separation in a hot cell. And we have already shown about 97% recovery. I think we could easily get to 99% recovery per cycle, which means that we could take the same gram and irradiate it maybe 30 to 50 times before we have to go and get fresh material. That's one point. But even more importantly is I think we can say that there's a whole world beyond radiochemistry where really people just gave up because there wasn't the possibility of doing anything with that. For example, I pointed out that the cross-section of making lutetium-177, if you could use lutetium-176, you get a factor of 700 times larger cross-section. So it means that a very scarce resource in the world are neutrons. That's another scarce resource. That's a different story. So you want to use them as efficiently as possible, and this would be a way to do that. And we think we can separate lutetium-177 from the 176 and the metastable state. You can sort of go through the periodic table and find all these solutions that people had not considered before. And I think this will be a powerful tool once we're on this track. Once at lutetium, I said about Moly-99 for making technetium-99M is a big deal. It's used for medical imaging, about 30 million scans per year in the US alone. That's 1 per second. And there's a real shortage of technetium-99M. And we have a pathway using Moly-99 from Moly-98 or Moly-100. And you can go down and the only thing, I won't go through the details, but just look, the red is the radioisotope and the green is the stable isotope. And you can see that in every line they're the same element. And that is not possible with radiochemistry. So I think this will be really transformative. In the projects that we have, these are some of the projects. If you go to the website of the Pointsman Foundation, you can read about our current projects. And I don't have much time, so I'll just say a little bit about prevention of iron deficiency and fundamental physics. So iron deficiency is something that affects over 2 billion people in the world, about 50% of children in developing countries. If a child between the age of after breastfeeding till the age, say 4, where their brain is developing, they don't get sufficient iron, they suffer permanent brain damage. Their whole life is essentially ruined. So this is really, really important. And iron is not easily absorbed, so you have to be sure that even though you give an iron supplement, is it really bioavailable? So how do you assess this bioavailability? Well, again, a historical diversion is that this was already recognized many years ago. And John Lawrence, the brother of Ernest Lawrence, they were making radioisotopes, so he took iron-59, which has a 44.5-day half-life. They actually gave it to toddlers and then took a blood sample, literally with a Geiger counter, to see if the blood was hot. You're not going to do that today, of course. But what we do today, and this was actually pioneered by our board member, Steve Abrams, was to enrich stable rare isotopes of iron, namely iron-57 and iron-58, and use these in fortification of food and beverage. But you have to do large-scale population studies. And the bottleneck has been that the price of these isotopes has been prohibitive. Iron-58 costs from calutron materials, about $200 a milligram, so $200,000 a gram. So that, you can't pay that, it's too expensive. Plus the plus the mass spectrometry is way too slow and a very expensive machine. So we believe that using our methods and MAGIS to separate iron isotopes and then ultrasensitive laser spectroscopy could be a scalable solution. But this is something which really would have to be paid for. So, all right. So finally, I think you have heard probably about many experiments that use isotopes. I'll just point out, and I won't have time to describe these in any detail, but just two examples of physics that are kind of interesting, where you can perhaps see new physics. In this case, both papers were proposed test of fundamental physics with atomic clocks. The first one is with radioactive atomic clocks. Suppose you have an atom like lutetium-177 or strontium-89 instead of, people use strontium-87, the most precise clock in the world, like Juni is running today, is strontium-87, but strontium-89 has a 50-day half-life. You could actually test some things about that. And a proposed test of quantum mechanics, which we proposed based on work by Steven Weinberg, who sadly passed away in 2021, but we actually built on that work to propose a real experiment. Finally, just to end, I wanted to point out that we have now in place a organizational structure. So the Pointsman Foundation is the parent organization. It's a nonprofit entity. We had to make a for-profit subsidiary for tax reasons and to shield the nonprofit from any liabilities. So we made a company, it's a C corporation called Pointsman Lab Incorporated, and it's owned 100% by Pointsman Foundation, and that will never change. But now we're starting to spin off for-profit subsidiaries which are also majority owned by, in this case, Pointsman Lab. Our first one is Atom Mines, but there will be a lutetium company and a molybdenum company and so on. Each one, I'm hoping that to achieve maybe 80 or 90% ownership by Pointsman Foundation, which will pay us, allow us to do things where there's no business model and to do other things. In particular, I want to cite this visionary paper by Steve, that Steve sent me, a paper that he wrote with Arun Majumdar in 2014. Was that when it was published? Bell Labs 2.0 for sustainable energy. This was a vision of making a new kind of Bell Labs. I think Steve called Bell Lablet or something. He could tell you the history better than I could. But anyway, I didn't know about this paper when I wrote a commentary in Physics Today entitled "Let's Recreate Bell Labs," and after that appeared, I guess at some point after that, Steve sent me his paper, which had really very similar ideas. I wasn't thinking just about energy sustainability, but that certainly should be included. But what we have, I believe, is a model, a for-profit, non-profit model, which would be sustained by our business plan for the isotopes. And so hopefully we have a way actually to pay for this and to really to do this. But we're working to try and get money by partnering with other foundations. We're in discussions right now with one of the world's largest foundations, which I hope will partner with Pointsman Foundation to accelerate this. Because once we really can start bringing in the income, then this will go a lot faster. And there is urgency for all these things. So I will end here, and you can look up what we're doing, www.pointsman.org, and thank you for your attention.
Wonderful talk, really elegant, great idea. I want to throw open for questions.
Mark, so how is different that separation from laser separation, which generally consists essentially in ionizing, resonantly an atom and then having electrostatic sort of potentials, which I think in small quantities works, but then they never manage to actually get to work on an industrial scale.
That's right. Well, the difficulty is that to photoionize, you have to climb a ladder, and the last step in the ladder is non-resonant because, well, you have to go to the continuum. So you could go to maybe an auto-ionizing state, so you might get some enhancement, but But generally, you need very high intensity, which you usually can achieve with a pulse laser. So I think it's just a matter of getting, getting sufficient intensity over large volumes. In our case, we avoid that because we can use low power, relatively low power, solid state lasers. So I think in terms of efficiency, it's working, but we don't really know. I mean, I would say laser separation that way has not really panned out as far as I'm aware.
The cross sections are much lower.
Right.
They're a multiple step. Not only is it multiple step, but going, imagine the optical cross section for a completely loud transition is humongous, like lambda squared over 2 pi. And
Right.
the ionizing cross sections are teeny, as well as multiple step.
Yeah.
Well, why don't you just
Yeah, very, very nice talk. It's great to hear how this Pointsman Foundation work is going. We talked about it a few years ago, and it seems to be much farther along. But I want to ask you a question about the basic physics of the first part of your talk.
Yeah.
I almost have to apologize for going back to that, but that.
That's fine.
I don't really understand whether you are thinking of these gas molecules or atoms as being collisional or collisionless. And the reason that I ask is that I wonder about M-changing collisions and how that would destroy the Maxwell's Demon effect.
Yes, you're right, and so there will be a density limit, especially for our MOP cooling when we have this all these different M states, and that's why it's hard for me to project what densities we could actually reach. I think what we envision is that this is the sort of thing that's going to be because a lot of these cross sections are not really known, but we can optimize in practice we can always expand adiabatically and to keep the densities low. And so it's a game we'll have to play, but you're absolutely right. Collisions are generally not desirable because they could lead to these spin changing collisions, and so we don't want collisions necessarily, really.
But you could use your demon, get them on the side, and then those expand them into lower pressure.
Right.
And so then you just turn it off.
Yeah, that's right. Steve.
Right now, are your lasers CW and the magnetic field CW?
Yeah.
And could there be advantage to going pulse?
Everything is CW for which? For the isotope separation?
Both.
Yeah, everything is CW.
What do you gain in that?
Well, the MOP cooling, the lasers are not pulse. They're AOM controlled. I wouldn't call it.
Deliberately synchronizing the atomic pumping portion with the drifting portion by working.
Well, in the MOP cooling where we collapse this, we actually will use pulse magnetic fields, and we learned a lot how to do that. We developed in my group back 15 years ago. We developed what we called a magnetic coil gun, where we took supersonic beam of paramagnetic atoms, and by timing we brought them to rest. So in doing that, we learned how to generate very large pulsed magnetic fields with switching currents of like 2 kiloamps. So we can impart kicks of like 10 or 20 meters per second. But for the isotope separation, we actually wanted something that will be as low energy consumption as we can get. So that's why we preferred just to use permanent magnets and low power diode lasers. So everything is on continuously. So it's kind of different. The two cases are different in that regard. Yeah.
So you said that your one-way wall is in actuality doing a sort of sorting as opposed to strictly speaking, as opposed to like cooling in the technical sense. Or maybe I misunderstood that. But I guess if that is the case, that you're doing sorting, can you also do cooling as well?
Well, I mean, compression in phase space is what we call cooling. I mean, cooling. Maybe you think about it as temperature, but you could if you can take atoms in a box and constrain them to half of the box, you can adiabatically expand the wall and go back to your original size box, and they'll be at a lower temperature. So you can always play that game, but you're not changing phase space when you do that. But what we are doing is exactly what Maxwell wanted to achieve. Yes?
Well, you know, if it really is going to be effective, collisions will be a problem.
Oh yeah, yeah, and that's why I think towards the end, my feeling is that at the very end, we probably will need to do evaporation, which relies on collisions at the very final step of getting to degenerate gases. But we don't know yet. Yes?
Thank you for the wonderful lecture. It was really great. I loved it.
Thank you.
But you mentioned that you could use it to test some unifications, I guess, of quantum mechanics and general relativity. Could you expand on that a little bit?
Okay, well, the theory is something that was developed by a number of theorists who we are collaborating with. They have a paper, I don't have the reference handy right now, but they wrote a paper where they analyzed the effect. It's essentially, they claimed that if you had a condensate, a Bose condensate, you could do quantum state tomography, so you could actually measure the Wigner function. You'd see a negative Wigner function, which would be a signature of what they call non-Gaussianity. And this is probably just gibberish right now. I don't understand it well enough to really explain it. So, it's a peer-reviewed paper, and I think it's credible. So I have to trust them on that. But from the experimentalist standpoint, we have to. I think our first task is to even get these numbers as high as we hope we can, and try to do these experiments. But that's generally what. And so that's in a nutshell what it is. Yeah. Other questions?
Great talk, and I'm enthusiastic about your isotope separator. What's the experimental status of the iron separator?
Oh, okay. Well, we are actually funding through the foundation. We've received enough philanthropy for the iron we are not yet building an ion separator, because that's not the sort of thing I want to do at the university, because there's a lot of trade secrets which we have to keep. University is a completely open environment, but we are working on we actually have an experiment to do ultrasensitive iron spectroscopy, and we are measuring that. We are working on some ideas which I can't talk about yet, but maybe in 6 months I could say more. If they pan out, they could actually lead to a big improvement of sensitivity of spectroscopy, which will be beyond iron. But for iron, we have a strong motivation, because ultimately one wants to take a very small blood sample from a toddler, so you don't want to do a venous draw, which is usually what is required, but rather a heel stick where you're just taking a few drops of blood. And so really getting the sensitivity higher has some strong motivation. So that's what we're working on now.
Well, Maureen, I have a question. Suppose you did strontium-2 isotopes, different hyperfine levels, different nuclear physics. Since you can measure 22 decimal places, relatively even better, would that be a good test of whether electromagnetic and nuclear interactions are changing?
That's what we want. That was the proposed paper that I wrote with Surjit Rajendran and
Too late.
But so actually, the paper, I was happy that the editors let us keep the title. The title was "Do Atoms Age?" ? And it actually is to look exactly at that, where the clock would be sensitive to nuclear physics, what's going on in the nucleus.
Yeah,
and I thought
coupling through the hyperfine.
Right, exactly. I thought about this for a long time, but I never dared write a paper until I ran into these two theorists who have a theory that actually predicts an effect. But it's worth testing, because it's not that hard to test.
Yeah, I wouldn't
rely on
the theory, but
but it gave me some respectability. Otherwise,
you don't need experimental test doesn't need any theory.
Yeah, but I think it is worth testing, and we could produce some of those isotopes, like strontium-89 or an alpha emitter would be interesting. We don't know, but it's an untested. We don't really have a good model of the nucleus. Because QCD is non-perturbative. So what's really going on in a radioactive atom? Is there some nuclear rearrangement that's happening? So the these extreme precision of atomic clocks may, I think it's at least as well motivated as searches for possible time variation of the fundamental constants. But here you have an extra knob, and that is the half-life. So you can really try that.
How much do you think it would cost to separate a mole of some of your elements? Dollars. You mentioned, like hundreds of thousands of dollars per gram.
Well, no.
No, not for your stuff, for the COLLOQUIUM.
Oh, right now we are charging that just because that's what we can. But in the long term, our costs, aside from the capital costs, which are the investment, the actual running costs are like 1,000 times, hundreds of 1,000 times less. So it could be a lot less expensive. But I don't think that's really not the driver. Cost is somewhat important, but the problem is in the supply chain. There's a pyramid where you have the stable isotope, and it sounds like a lot of money, but then the radioisotope is a 20x on top of that, and then the radiopharmaceutical is 20x times more. So you have a 400 times, so even if you could make the stable isotope cheaply, in the end Novartis is going to want to charge whatever they charge for the radiopharmaceutical. It's not going to bring down the cost of the...
Also the 20x for the doctor.
Well, yeah. But I think the problem is if it's not available, then...
Right. Actually, while you were talking, I was thinking, we talked about possible foundations. Are you doing Chan Zuckerberg as well?
No, I don't. One needs an introduction, more introduction.
I can help.
Okay, great.
I failed with the others. So
okay, well that would be great. Yeah.
Any other questions? Okay. Well, thank you very much.
Thank you.
They might, because Priscilla Chan's a doctor.
Yeah.
She's very